Dear students, today we are going to study the first unit, wave optics. In the first unit, the first topic is interference. As you have studied in your class 12, what is interference? Interference is overlapping of superposition of two or more than two waves. Two or more than two waves, okay? There are two types of interference, constructive interference and destructive interference. I will go step by step and will let you know what are the features of constructive and destructive interference in the whole chapter. So, the first topic of the interference is Newton's rings. As you can see in the notes, the diagram is drawn here. I will explain the diagram on the board in my next lecture. First, I will explain the theory part that is written in the notes. Newton's rings. Newton's rings are interference pattern produced in the circular wedge-shaped air film formed between a plain glass plate P and a plano-convex lens L. So, what is a circular wedge-shaped air film? First, I will explain you how the circular wedge-shaped air film is formed between a plain glass plate P and the plano-convex lens L. As you can see in the diagram, the plate P and a plano-convex lens L. For the convex lens, both the parts are convex in nature, but for the plano-convex lens, one part is plane. Between the plain glass plate and the plano-convex lens, a circular air film is formed. Why the air film is circular? Because the shape of the plain glass plate and the plano-convex lens we have taken is circle. One more thing I would like to tell you that we take the plano-convex lens of large radius of curvature. Why do we take it for large radius of curvature? I will explain you later on after deriving the formula of radius of the fringes. So, Newton's rings are interference pattern produced in the circular wedge-shaped air film. The wedge-shaped air film is formed between the plain glass plate and the plano-convex lens. When this system means plain glass plate and plano-convex lens and the air film between those, this is illuminated from a broad extended source of light. We take here a sodium light source as broad extended source of light. Sodium light source is a monochromatic light source. As you know that the monochromatic light source is a light source that gives you the light of single wavelength or single frequency. When the light falls on the glass plate which is inclined at an angle of 45 degree, you can see that a glass plate is here which is inclined at 45 degrees angle. When the light is incident on this plate, it is reflected. The light is reflected normally onto a plane convex lens L. You can see I will explain this diagram on board in my next lecture. So you can see that the light is incident normally on the plano-convex lens L. Now, why the pattern of the fringes is circular? This is because due to the circular symmetry of the wedge-shaped air film above the point of contact, means where the plano-convex lens and the plane glass plate, they both touch each other. That point is called the point of contact. So around the point of contact, the air film, the wedge-shaped air film, is of circular nature. So, due to the circular symmetry of this wedge-shaped air film about the point of contact of the lens with the glass plate, the locus of points on the surface of the air film where the thickness of the film is same is a circle. Means the surface of the air film where the thickness of the film is same is a circle. So, these circular fringes are called Newton's rings. You can see that the light is incident on a plain glass plate at an angle 45 degree. After reflection, they are incident to the system of plain glass plate and plano convex lens, and between those there is a air film, and you can see that you have two reflected waves that are meeting at the microscope. Between these waves, the superposition held and you get the interference pattern, and the interference pattern is of you get is circular in nature. So the next topic is Newton's rings in reflected light. You can see the diagram for the reflected light. First of all, we have to consider the path difference between the rays R1 and R2. I will explain this diagram on board in my next lecture. The path difference between the rays AR1 and BCR2. As you know, when the interference occurs, whether it is constructive interference or it is destructive interference, there is a certain path difference between the waves. If the path difference between the rays follows the condition of constructive interference, then you get maximum intensity. If the rays follows the condition of destructive interference, we get the zero intensity. I would like to tell you that the path difference between the rays R1 and R2, the reflected rays, the path difference comes out to be 2 mu t. This is the formula that we derived in class 12th. So you have to remember this formula, that the path difference between the rays R1, AR1 and BCR2 is equals to 2 mu t. T is the thickness of wave film at the point of reflection, and mu is the refractive index of air film. For air, mu is equals to 1. You know the refractive index of air is 1. T is the thickness of the air film at the point of reflection. As one of the rays suffers reflection at a denser medium, means at B, uh, so there is a phase change of pi, or path difference of lambda by 2 takes place. Means you have two reflected rays, AR1 and BCR2. We can see that the ray from B is getting reflected by the denser medium, and the ray AR1 at point A, the ray is getting reflected from the rarer medium. So there is a phase difference of pi, or you can say the path difference of lambda by 2 takes place here. Do you know the formula between the path difference and the phase difference. I would like to remind you the phase difference is equals to 2 pi by lambda multiplied by path difference. You have studied this formula in your class 11th. The phase difference is equal to 2 pi by lambda multiplied by path difference. So the total path difference comes out to be 2 mu t plus minus lambda by 2. As you know, the condition of destructive interference, the path difference equals to n plus minus half lambda. You have studied this formula in your class 11. For destructive interference, the path difference is equals to n plus minus half lambda. So here the total path difference is 2 mu t plus minus lambda by 2 is equal to n plus minus half lambda. So the formula comes out to be 2 mu t is equals to n lambda. Here you get t n is equals to n lambda upon 2 mu. For constructive interference, the formula for constructive interference, as you have studied earlier, for constructive interference, path difference should be equal to n lambda. Now, what is the total path difference here? The path difference produced by the air film between the rays AR1 and BCR2. The path difference is 2 mu t plus minus lambda by 2. How did you get 2 mu t? The path difference produced by the air film. How did you get lambda by 2? Because one of the ray is getting reflected from point A and one of the ray is getting reflected from point B. One is getting reflected from denser media and one is getting reflected from the rarer media. So for constructive interference, the total path difference 2 mu t plus minus lambda by 2 is equals to n lambda. So 2 mu t is equals to n plus minus half lambda. Okay. Now we will derive the formula of diameter of dark and bright fringes. You can see the diagram. Here capital R is the radius of curvature of the plano-convex lens and C is the center of curvature. Point O is point of contact of lens with glass plate P. Tn is thickness of air film at a particular point. At the point capital A, where nth interference fringe of radius Rn is equals to Ea is formed. You can see what is capital R? Capital R is the radius of curvature of the plano-convex lens. What is C? C is the center of curvature. What is O? O is the point of contact of lens with glass plate P. Tn is the thickness of the air film at point A. In my next lecture, I will explain these three diagrams on board. So please keep watching the lectures.